Imagine the universe as a story with a final chapter we haven't read yet. The opening lines are pretty clear. Space is expanding, galaxies are moving apart, and the overall behavior of the cosmos is governed by a few simple-sounding things. How much stuff there is, how strongly gravity pulls, and something stranger called dark energy that seems to be pushing everything outward. But those few facts can lead to wildly different endings. Some of those endings are oddly gentle and unimaginably slow, others are violent and sudden, and a few are the kind of scenarios that make you check the locks twice. Let's walk through the main candidates scientists have come up with, in plain language and with everyday analogies, so you can picture what each doomsday would actually mean. First, a quick, intuitive foundation. When we say the universe is expanding, picture a loaf of raisin bread rising in the oven. The raisins are like galaxies. As the dough expands, raisins move away from each other. No raisin is the center of the loaf. Expansion just increases the distances between raisins. That expansion was discovered by observing that light from distant galaxies is stretched. Their light shifts to redder colors, and more distant galaxies shift more. If we know how fast and how that rate changes over time, we can start to predict the future. The twist that makes everything interesting is something we only learned late in the 20th century. The expansion is speeding up. Instead of gravity slowing the expansion, something dark energy is accelerating it. It's as if unseen hand is quietly turning up the rate at which the loaf puffs. The simplest explanation for dark energy is a constant energy density of space itself, sometimes called the cosmological constant. But whether it's truly constant or changing or something even stranger matters enormously for the universe's fate. The Big Rip, when the stretching gets violent. Start with the scariest sounding one, the Big Rip. In this scenario, whatever is causing acceleration doesn't just push, it grows stronger over time. Imagine that the stretchy dough keeps expanding, but the internal pressure also climbs. So the raisins not only move apart faster, but the forces holding the raisins together start to be overcome. Over a long enough period, the inward forces that bind structures, galaxy clusters, galaxies, solar systems, planets, atoms, would fail one by one until even atoms themselves are torn apart. How would that play out step by step? If a big rip were in our future, it wouldn't be a sudden instant but a sequence. First, galaxy clusters would drift apart. Gravity would no longer be able to hold the largest bound structures together, so clusters of galaxies would disassemble. Next, individual galaxies would fall apart. Stars would no longer orbit stably in coordinated motions, because the expansion would overwhelm the gravitational glue. Then star systems, including ours, would disintegrate. The planets would be pulled away from their stars. Eventually, the bonds holding planets together could fail. After that, molecules and atoms would be stretched and ripped apart, and finally the subatomic structures inside atoms could be undone. Think of stretching a rubber band that gets more and more elastic. At some point, the forces in the rubber can't hold and it snaps. The big rip happens if the energy-driving expansion has a property that makes its density increase as the universe expands, effectively producing more ripping power the further things stretch. In the usual language of cosmology, there's a number called W, a way to describe how this energy behaves. If W is less than -1, you get phantom energy and the big rip. If it equals -1, that's the cosmological constant, no rip. If it's greater than -1, you get other behaviors, usually more peaceful. How likely is it? Observations so far don't demand a big rip. They are consistent with W being very close to -1, which means a steady dark energy density. That leads to a forever expanding universe, but not necessarily a violent rip. Still, measurement uncertainties leave wiggle room. If W turns out to be just a bit below -1, the big rip could be real. And if so, the timescale matters. Some toy models predict a rip many billions of years from now, so distant that it's hard to imagine, while others could give different timings. Right now, the big rip is a fascinating possibility, but not the default story. Heat death, aka the big freeze, a long, cold silence. If the Big Rip is the violent end, heat death is the slow fade. This is the version favored by the simplest interpretation of current observations. Dark energy that behaves like a true cosmological constant, keeping expansion accelerating but not growing in strength. The basic idea comes from thermodynamics. Systems tend to move toward states where energy is spread out as evenly as possible, higher entropy. A hot cup of coffee loses heat to its surroundings until it's the same temperature as the room. The universe, left alone, evolves toward a state in which usable energy is maximally dispersed and no more work can be done. What does no more work can be done mean on cosmic scales? It means stars stop forming because the raw materials are too thinly spread. Existing stars burn out and die. Black holes eventually evaporate through quantum processes. And gradually the universe becomes a sparse, cold soup of low-energy particles, with enormous stretches of truly empty space between them. Over unimaginably long timescales, even protons might decay, depending on whether that process actually happens. And the last remnants of organized matter could dissolve into radiation and elementary particles. Try the following analogy. Imagine a marble at the top of a gently sloping hill rolling down. It loses the ability to do useful things as it settles into a valley where it can't go anywhere interesting. Or think about batteries gradually losing charge until none of them can power a light bulb. In heat death, all the cosmic batteries are drained. Here's how the timeline might look, in rough, enormous steps. In the next tens to hundreds of billions of years, star formation will slow as galaxies run out of raw gas. The bright, star-forming era will come to an end. Over maybe 10–14 years, most ordinary stars will have burned out. White dwarfs, neutron stars, and black holes will be left a dim, cold universe. Over vastly longer times, black holes evaporate by a process called Hawking radiation. The smaller the black hole, the faster it evaporates. Supermassive black holes take up to about 10–100 years or so to vanish, depending on their mass. After black holes evaporate, the universe will mostly be low-energy photons, neutrinos, and perhaps some stable relics. If protons decay, that's another route to leaving only radiation and light particles. After incredibly long timescales, everything that can happen has happened. The universe is smooth, cold, and maximally entropic, heat death. This is often called the Big Freeze because the temperature asymptotically approaches absolute zero, but never quite reaches it, and nothing interesting, at least by the standards of stars and chemistry, remains. An unsettling philosophical twist appears here too. In an eternally expanding, maximally entropic universe, random fluctuations over truly colossal timescales could build local pockets of lower entropy by sheer chance. That's where the Boltzmann brain thought experiment comes in. Given enough time, random particle fluctuations could assemble a brain that briefly has memories and perceptions. If the universe lasts forever, it might produce vastly more such freak observers than observers who evolved through ordinary processes, raising thorny questions about how to interpret probability in cosmology. The idea is more of a conceptual puzzle than a strictly physical threat, but it does feel like existential vertigo when you think about it. The Big Crunch, gravity wins. The Big Crunch is the intuitive opposite of expansion. Imagine the expansion slowing, stopping, and reversing, until everything collapses back into a hot, dense state, essentially the Big Bang run in reverse. In older cosmological thinking, this was a natural possibility. If the density of matter in the universe were high enough, gravity would eventually slow and then pull everything back together. If the universe were heading for a big crunch, what would happen? The current expansion would halt and reverse. Galaxies would approach one another. Collisions and mergers would be increasingly violent as time went on. As everything compresses, temperatures rise, radiation becomes dominant again, and matter breaks down into an ultradense, hot state. Eventually, the universe could end in a singularity, a point of infinite density, similar to how the standard Big Bang is usually described at the origin of time. There are modern twists on this, though. Some speculative models replace the singularity with a bounce. The universe collapses and then, under exotic physics, bounces back into a new expansion phase. Cyclic models have been proposed where universes undergo endless sequences of expansions and contractions. Some versions invoke higher dimensional interactions or other mechanisms to avoid a singularity. However, with the discovery of cosmic acceleration, the Big Crunch lost favor because acceleration implies that the universe is moving away from the conditions that lead to a collapse. To get a crunch today, you'd need one of these. The dark energy could change behavior over time. It might be temporary and reverse sign, letting gravity win later. The geometry or matter content of the universe might be different than we think, but current observations of the cosmic microwave background, galaxy clustering, and supernovae suggest a flat geometry with a cosmological constant like dark energy, which points away from a crunch. Still, if dark energy evolves, nothing strictly forbids a collapse. Big crunch scenarios are less fashionable now, but they're conceptually straightforward and occasionally show up in models that explore new physics. False vacuum decay. A silent, instant end, this one is less intuitive and more unsettling in a different way, because it could be abrupt and leave no trace of warning. The idea comes from quantum field theory. The fields that determine particle masses and forces can have complicated energy landscapes. Your system, in this case, the patch of the universe we live in, might be sitting in a false vacuum. A local energy minimum that looks stable but isn't the absolute lowest energy configuration available. Analogy time. Picture a shallow bowl sitting on a shelf beside a deeper bowl. A ball in the shallow bowl seems stable, but if it could somehow get over the ridge separating the bowls, it would fall into the deeper bowl and sit at a lower energy. Quantum mechanics allows things to tunnel through barriers that would be classically forbidden, so over extremely long times there's a chance the ball will disappear from the shallow bowl and appear in the deep one. If our universe is in a false vacuum, and a transition to a lower energy true vacuum occurs somewhere, it would start as a bubble that expands at nearly the speed of light. Inside that bubble, the laws of physics, particle masses, the strengths of forces, the values of fundamental constants could be different. Anything that enters the bubble would be destroyed and reconstituted according to the new laws. Because the bubble wall travels at light speed, we would have no way to detect it in advance. By the time light from the event reaches us, the bubble would already have reached us. The universe as we know it would be gone. Is there reason to think this could happen? Measurements of the Higgs boson mass and the top quark mass have led some calculations to suggest that our current vacuum might be metastable. Those calculations are sensitive to precise values and to unknown physics beyond the standard model, so they're not a smoking gun. In many reasonable scenarios, the lifetime of a metastable vacuum is astronomically larger than the current age of the universe. But quantum tunneling is probabilistic. Astronomically large is not the same as impossible. The unsettling thing is that this kind of end would be instantaneous and leave no gradual signs. It's a genuine doomsday possibility that physicists take seriously enough to compute lifetimes and consider implications. Bubble collisions and multiverse scenarios related to false vacuum decay are ideas about a multiverse where different regions have different vacuum states. In some inflationary cosmology models, bubble universes nucleate with different properties. Collisions between bubbles could, in principle, affect our region. If another bubble with different physics were to collide with ours, the outcome could range from benign to catastrophic, depending on the difference. These ideas are speculative and brush against deep philosophical questions about testability and prediction. Still, they can be framed in physical terms. Different local minima in a landscape of possible vacua can lead to distinct regions with distinct low-energy laws. If those regions collide, the interface could be violent. The observational challenge is that if such events are rare or happened in the very early universe, their signatures might be subtle or undetectable now. Quantum instability and random fluctuations at the smallest scales, quantum mechanics makes the vacuum a restless place. Even in empty space, particle-antiparticle pairs flicker into and out of existence. Over unimaginably long timescales, unlikely fluctuations could, in principle, produce macroscopic changes. For instance, it's sometimes discussed that a sufficiently rare but large fluctuation might create a high-energy state that leads to vacuum decay. Most such considerations are academically speculative, and calculated probabilities are usually small. But when we're talking about timescales like eons beyond human comprehension, small can still be conceptually meaningful. What makes these quantum pathways especially unsettling is their unpredictability. They don't require a change in the large-scale parameters like density or expansion rate. They're driven by the fundamental uncertainty built into quantum fields. So even if the universe appears stable on every cosmological scale, quantum instability raises the theoretical possibility of sudden change. Observational clues and what we actually see given all these scenarios. What does the data say? Over the past few decades, astronomers have accumulated several independent lines of evidence that the universe is flat in the geometric sense, and that the expansion is accelerating in a way consistent with a cosmological constant, a constant energy density per unit volume of space. Key elements of that evidence include the redshifts and brightnesses of distant Type Ia supernovae, which first revealed acceleration in the late 1990s. The cosmic microwave background, the afterglow of the Big Bang, which encodes information about geometry and matter content. The distribution of galaxies and the characteristic scale imprinted by sound waves in the early universe, baryon acoustic oscillations. Taken together, these observations form the backbone of the lambda-CDM model, lambda for the cosmological constant, CDM for cold dark matter. Lambda-CDM is remarkably successful at explaining a wide range of observations. Under this model, the most likely long-term fate is heat death. The universe expands forever, structure formation winds down, and the cosmos cools. That said, the true nature of dark energy is still one of the biggest mysteries in physics. The cosmological constant is the simplest hypothesis, but physicists are actively searching for deviations. If dark energy changes with time, or if some completely different mechanism underlies acceleration, the cosmic endgame could be altered. Observations continuing over the coming decades and better measurements of parameters like W will help narrow the possibilities. Timescales. The scales are so large they're almost absurd. One of the most mind-bending things about cosmic doomsdays is their timescale. Human history occupies mere milliseconds compared to these spans. Here are some rough numbers, always to be taken as order of magnitude thinking, because they depend on details and unknown physics. The Sun will become a red giant and render Earth uninhabitable in roughly 5 billion years. That's local stellar evolution, not cosmic death. Star formation will largely cease on timescales of 1012 to 1014 years as galaxies run out of gas. Black holes evaporate by Hawking radiation. Small black holes evaporate faster. Stellar mass black holes live far longer than stars. Supermassive black holes in galaxy centers could take around 10–100 years to evaporate. If protons decay, a possibility in some particle physics theories, their half-life would be at least around 1034 years or longer, pushing many decay-driven endpoints far into the future. But proton decay remains experimentally unobserved. Heat death, the effective end of structure, is discussed on timescales vastly longer than 10–100 years, depending on the processes involved and what decays occur. Big Rip scenarios can have much shorter timescales relative to the age of the universe in some models, potentially tens of billions of years. But again, that depends on the dark energy behavior. Vacuum decay lifetimes, as derived from current measurements, could be far longer than the age of the universe, but the exact numbers hinge on unknown high-energy physics. These numbers are not precise predictions in the way you might forecast the weather next week, but they give the flavor. Cosmic endings play out on timescales that dwarf the lifespan of stars, planets, and civilizations. Practical effects and human perspective, it's tempting to treat these scenarios like impending threats you can prepare for. But the truth is that most of them occur over time, spans so enormous that they have no practical relevance to current human concerns. The exceptions are local events like the eventual death of the sun or far future hazards like close passes from wandering stars on the timescale of billions of years, not cosmological endings. We won't be able to stop a vacuum decay or change the cosmological constant by engineering. That said, thinking about cosmic endings is useful in other ways. It pushes physics to its limits, forcing us to confront questions about quantum fields, gravity, and the deep structure of space-time. It also reframes the preciousness of the present. Our window to understand the universe is finite and on cosmic timescales tiny. If the most likely fate is a quiet heat death driven by a cosmological constant, then what we can learn and observe now, the cosmic microwave background, the large-scale structure, the chemistry of life, is a rare opportunity in the universe's history. Alternatives and hybrids, more strange possibilities. Cosmology is a field with room for creative theories. Some alternatives blend elements of the major endings or rely on new physics. Cyclic universes. Instead of a final end, the cosmos undergoes repeated expansions and contractions. These models need mechanisms to reset or avoid the entropy buildup problem that normally makes cycles get noisier and less viable. Bounce models. A contracting phase ends not in a singularity but in a bounce, perhaps due to quantum gravitational effects, creating a new expansion. These ideas draw on speculative physics like loop quantum gravity or string theory. Interacting dark energy. If dark energy interacts with dark matter or changes character, the ultimate fate could be altered, from reversal of expansion to complicated oscillatory behaviors. Big slurp, a phrase sometimes used for false vacuum decay, emphasizes the sudden vacuum swallowing image. Brain collisions. In models inspired by extra dimensions, our universe could be one membrane brain floating in a higher dimensional space. Collisions with other brains could have dramatic consequences for the physics inside the brain. Most of these are deeply theoretical and currently lack decisive empirical support. They serve as playgrounds for theoretical physicists trying to reconcile gravity with quantum mechanics or to understand the landscape of possible universes. What would we see if the end were NEAR? Different ends would have different signatures if we were looking closely. For a big rip, if it were imminent on cosmological timescales, we'd see large-scale structures unbinding, galaxies dispersing their stars, and orbital systems breaking down. The key would be a measurable change in the expansion rate that accelerates with time beyond the cosmological constant prediction. For heat death, it's not dramatic. We'd observe a gradually thinning cosmos. Fewer bright galaxies, cooling black holes, and a decline in star formation. From a human perspective, there's no last-day flash, it's a slow fade. For a big crunch, we detect a deceleration of expansion, then contraction. Background radiation would heat up, galaxies would move together, and the sky would grow denser and more chaotic as everything compresses. For vacuum decay, there's basically no early warning. A bubble forming somewhere beyond our causal horizon could be expanding for eons. When its wall reaches us, it would arrive at light speed, and the change would be instantaneous from our observational standpoint. Right now, the data align most closely with the slow fade picture, but that conclusion is conditional on dark energy being a cosmological constant. The scientific value of doomsday thinking. Why do scientists spend time thinking about what seems like fantastical endings? There are several reasons. Testing physics. These scenarios push our theories to extreme conditions, ultra-low densities, extremely long times, near-vacuum quantum tunneling, where competing ideas make distinct predictions. Constraining unknowns. Observational programs aimed at measuring dark energy properties or testing for tiny changes in fundamental constants can rule in or out classes of endings. Conceptual clarity. Thinking about end states helps clarify what we don't know and what assumptions underlie our models. Philosophical questions. Long-term fates touch on issues in probability, observer selection, and what constitutes typical experience in the universe. Where practical, instruments and surveys aim to pin down the key parameters that determine the future. Projects that map the large-scale structure of the universe, observe more Type Ia supernovae, and measure the cosmic microwave background with increasing precision are all part of this effort. Open questions that matter for the outcome. A few unknowns are especially consequential. The true nature of dark energy. Is it a cosmological constant or something dynamic? Does it interact with other forms of matter? The stability of the vacuum. Are we in a true ground state or only a long-lived metastable state? How do the Higgs boson and top quark masses influence that conclusion? The validity of known physics at high energies. New particles or interactions beyond the standard model could alter decay rates, stability, or cosmic dynamics. Whether protons and certain other particles actually decay, this would change the late-time inventory of matter. Pinning these down would dramatically reduce the range of plausible futures. For instance, if high-precision cosmology shows that W is exactly -1 to all measurable precision, a big rip would become extremely unlikely. If collider experiments or theoretical developments reconfirm the metastability calculation for the vacuum with higher precision, the false vacuum route would either gain or lose plausibility. The human story. Stories we tell about the end, different endings, tap different deep fears and curiosities. Some, vacuum decay, are frightening because they're sudden and invisible. Others, heat death, are sobering because of their absolute, final quietness. Big Crunch endings echo myths of cyclical destruction and rebirth. Big Rip scenarios have a distinctly visceral quality. Things being torn apart in a sequence you can imagine in stages. These narratives also shape how we think about our place in the universe. If the cosmos is headed toward heat death, the present period when structure, stars, and complex chemistry are abundant becomes historically precious. If the vacuum is metastable and could flip unpredictably, our universe feels fragile in an even deeper way. If the universe will bounce or cycle, then endings are only beginnings in a grander sense. None of this changes immediate human concerns, politics, family, personal plans, but it does anchor us in a larger context. Scientific exploration of these fates is not morbidity for its own sake. It's a way of testing our theories about how nature works at the most fundamental level. With that groundwork laid, we can now dig deeper into the physics behind each scenario, look at the concrete evidence for and against them, and consider odd edge cases and philosophical puzzles they raise. We've laid out the headline scenarios: Big Rip, Heat Death, Big Crunch, Vacuum Decay. Now let's get under the hood and see what physics actually drives those endings, what we can measure, and what remains guesswork. The purpose here is not to swamp you with equations, but to show the simple mental pictures scientists use, what observations can tell us, and where real uncertainties hide. Start with the thing that steers almost every ending: how the energy content of the universe changes as space expands. Cosmologists summarize that behavior with a small set of numbers and a few simple concepts. One of the most useful knobs is called W, which is a way of describing how pressure relates to energy density for the component we call dark energy. If W equals -1 exactly, dark energy behaves like the cosmological constant. Its energy density per unit volume stays the same as the universe expands. If W differs from -1, dark energy behaves differently. If W-1, it's less negative and could dilute or change. If W-1, it behaves oddly. Its energy density increases as space expands, which opens the door to big rip-type outcomes. A handy analogy is to think about different fluids in an expanding balloon. Some fluids thin out as the balloon grows, like normal matter or radiation. Others, like a special substance smeared throughout the balloon, might keep the same density no matter how big the balloon gets. The cosmological constant is that stubborn substance. Quintessence is like a fluid whose density slowly changes as the balloon inflates, its pressure and density evolve with time. Phantom energy, the stuff behind the Big Rip, would be a hypothetical fluid that somehow becomes denser as the balloon grows, eventually building up destructive force. What distinguishes these options observationally is how they affect the expansion history and the growth of structure. If dark energy evolves, distances to faraway objects and the way galaxy clusters form will look different from the constant case. That's why modern cosmology is essentially an observational campaign to measure the expansion history as precisely as possible. Astronomers use Type Ia supernovae as standardizable candles, the original evidence for acceleration. The cosmic microwave background to measure geometry and early universe parameters, baryon acoustic oscillations as a cosmic ruler, and gravitational lensing in galaxy surveys to track structure growth. Instruments and projects actively on the job include ground-based surveys and space missions. Think of Euclid, the Roman Space Telescope, DAISY, and the Vera Rubin Observatory, all aimed at pinning down W to a percent-level precision or better. The tighter those constraints get, the more we can favor or rule out alternatives to the cosmological constant. But measuring W is tricky. The parameter can vary with time, and observational uncertainties and systematic effects complicate precision. Current data are consistent with W equals -1 within a few percent, which is why lambda CDM, cosmological constant plus cold dark matter, remains the standard model. It's also why, barring surprises, the heat-death picture is the default scenario, a forever expanding, cooling universe where structure fades. Still, small deviations could matter enormously. A tiny measured tilt toward W-1 would rekindle interest in phantom models and the Big Rip. A shift toward a time-varying W could imply quintessence or even interactions that reverse expansion in the far future. What does quintessence look like in plain terms? Imagine a field. Think of it like an invisible, space-filling substance with potential energy, rolling slowly down a gentle slope in an energy landscape. The slope sets how the energy density evolves. If it's very flat, the field hardly changes and acts like a near-constant cosmological constant. If the slope is steeper, the field rolls, the energy density changes, and so can the expansion rate. Quintessence is appealing because it offers dynamics. It's one way to imagine dark energy as part of a larger, evolving story rather than a fixed backdrop. But fields that roll need to be ultralight and interact weakly with ordinary matter, which makes them fiendishly hard to test directly. Their fingerprints show up mainly in the large-scale expansion history and in subtle effects on how structure grows. Phantom energy, exotic stuff with W-1, is stranger. It violates one of the energy conditions that physicists have used for decades to keep gravity behaving sensibly. In simple terms, phantom energy corresponds to a field with negative kinetic energy in some models, which invites instabilities and theoretical headaches. That doesn't mean phantom energy is impossible, but it does mean most theorists treat phantom models with caution. If the universe were dominated by phantom energy, the energy density would grow as space expands, and the eventual ripping apart of bound structures would follow. Observationally, the signature would be a very particular acceleration pattern. Expansion that speeds up faster and faster in a way that can't be mimicked by a cosmological constant or gentle quintessence. Now switch gears to vacuum stability and false vacuum decay, because this is where quantum mechanics and particle physics collide with cosmology in the most dramatic way. The vacuum in quantum field theory is not empty space in the naive sense. It's the lowest energy configuration of fields. That lowest energy state could be an absolute minimum, stable forever. Or it could be a local minimum, a false vacuum, separated from a true, lower energy minimum by an energy barrier. Quantum mechanics allows tunneling. There's a tiny but non-zero probability for the system to jump through the barrier. In field theory, such a tunneling event nucleates a bubble of true vacuum which then expands. How likely is that? The rate is exponentially suppressed, determined by the height and width of the barrier and by the shape of the potential. This suppression can make the lifetime astronomically large, far longer than the current age of the universe. But even a tiny chance per unit volume per unit time becomes conceptually meaningful if you allow arbitrarily large volumes and indefinite time. The most famous calculation of bubble nucleation in a gravitational setting is due to Sidney Coleman and Frank DeLucia. Their formalism lets you estimate bubble formation rates and includes gravitational effects. For our universe, people have looked closely at the Higgs field after the Higgs boson's discovery in 2012. Because the Higgs potential is exactly the kind of thing that could, in principle, have a metastable shape depending on parameters like the Higgs mass, the top quark mass, and the strong interaction coupling. Actual calculations using measured values show a curious borderland. The Higgs mass and top mass sit in a region where, within the standard model and without unknown high-energy corrections, the electroweak vacuum might be metastable. But might be is the key. The lifetime estimates for a Higgs-driven vacuum decay tend to be stupendously long, far longer than the current age of the universe, provided nothing else disturbs the situation. Those estimates are also sensitive to physics we don't yet know, like potential heavy particles or interactions at energies beyond what the LHC can probe. So while the metastability result is real and worth thinking about, it's not a looming menace in the practical sense. It is a deep theoretical point, though. Our apparent vacuum could be one local basin in a larger landscape of possibilities. If a bubble of true vacuum does form somewhere, its wall would accelerate outward at nearly the speed of light. Inside the bubble, the rules of physics could be different: particle masses, coupling strengths, even whether stable atoms as we know them can exist. For anything overtaken by the wall, the transition would be terminal and effectively instantaneous from its perspective. Because the wall moves at light speed, we could not receive warning signals from events outside our causal past. If a bubble nucleated far away, by the time we saw any light from the initial nucleation, it would already be too late. That's the unsettling, no-warning aspect physicists emphasize. Are there any observable precursors to vacuum decay? Directly, not really, by its nature, bubble nucleation is local and abrupt. Indirectly, precise measurements of parameters that control the potential, like those of the top quark in the Higgs, help refine the metastability picture. And if we did live in a cosmology where many bubbles nucleated in the early universe, bubble collisions could leave imprints, for instance, in the cosmic microwave background or in gravitational wave backgrounds, that carry telltale signs. People have searched for such signals, though none have been convincingly found. Let's return to entropy, black holes, and heat death, because entropy is where thermodynamics, information, and cosmology cross paths. The second law of thermodynamics, that entropy tends to increase, is the engine behind heat death. What does that mean when applied to the entire universe? In a universe dominated by a positive cosmological constant, the late-time geometry approaches a de Sitter space, an expanding spacetime with a cosmological horizon. That horizon has a temperature, the Gibbons-Hawking temperature, and an associated entropy proportional to the area of the horizon. Physicists often point out that a de Sitter universe has a maximum observable entropy set by that horizon. This creates conceptual puzzles. If there is a maximum entropy, how do you reconcile the notion of endlessly producing observers through random fluctuations? That's where the Boltzmann brain problem arises. The Boltzmann brain thought experiment goes like this. In a state of thermal equilibrium that lasts arbitrarily long, random fluctuations will occasionally assemble low-entropy configurations by chance. Given enough time, even a single brain with false memories could appear spontaneously. If the late-time de Sitter vacuum persists forever, and the entropy budget allows such fluctuations, naive counting may suggest that freak observers vastly outnumber ordinary observers who evolved in a low-entropy past. That creates a paradox about how to interpret probability and typicality in cosmological contexts, and has driven serious technical work on measures in cosmology, ways of regulating infinities and defining probabilities, so the paradox is avoided. The upshot is that questions about the end of the universe feed back into deep issues about prediction, typicality, and what we should expect to observe. Black holes are another entropy-rich ingredient. According to Hawking's calculation, black holes slowly radiate away their mass via quantum effects. The emission temperature is inversely proportional to mass, so small black holes radiate faster than large ones. Typical numbers that stick in popular accounts are: a stellar mass black hole evaporates over about 1067 years, while the supermassive black holes sitting at the centers of galaxies might take on the order of 10–100 years to vanish. Those are unimaginably long times, but they matter when sketching the far future. During the era when stars have burned out and normal matter is sparse, black holes become the last substantial reservoirs of organized energy. Their eventual evaporation spews out low-energy radiation that contributes to the cooling and dilution of the universe. If protons decay, another unresolved particle physics question, the inventory of long-lived matter changes dramatically. Proton decay would slowly convert baryonic matter into lighter particles and radiation, erasing the building blocks of chemistry over absurdly long timescales. Experiments like Super Kamiokande and its successors set lower bounds on proton lifetime at around 1034 years for certain decay channels, but direct evidence for proton decay has not been found. All of these late-time processes, proton decay, black hole evaporation, diminishing star formation, feed the heat death story. The key conceptual point is that heat death is not a sudden cataclysm. It's an asymptotic approach to a maximally mixed, high-entropy state where no useful work can be extracted. For creatures or devices that depend on gradients, hot/cold, concentrated energy versus background, no gradient means no functioning. That's why the heat death scenario feels emotionally different from violent endings. It's the end of doing, not necessarily the end of instantaneous existence. Some scientists and science fiction writers have wondered whether advanced civilizations could engineer ways around these limits. Items like the Dyson proposal to hibernate, or to use intermittent energy extraction to make subjective time stretch. Freeman Dyson once suggested that by decreasing activity and stretching out computations, a civilization could live forever in an expanding universe with ever-decreasing energy supplies. Later work, notably by Cross and Starkman and others, argued that once you include effects of a true cosmological horizon, a strict de Sitter end, and thermodynamic limits, many of those escape routes don't work. The total amount of usable energy available in such a universe is finite. In short, cleverness can buy you longevity, but not infinity in many cosmological models. These debates illustrate how cosmology interfaces with questions about computation, thermodynamics, and life's possibilities in the extreme. Let's talk a bit about the big crunch and cyclic ideas, since they open up alternative mental pictures. The big crunch requires gravity to win over expansion at some point. That would happen if the universe's energy budget were configured so that the net long-term pull dominated. That's not what our current data indicate, but it's possible in principle if dark energy fades or reverses. Some speculative cosmologies take this further and propose cyclic universes. The universe expands, contracts, and then re-expands in a series of bounces. These ideas date back a long way and have modern formulations drawing on extra dimensions and string theory, or on quantum gravity proposals that replace classical singularities with bounces. Cyclic models face significant challenges, most importantly making sure that entropy doesn't accumulate and ruin subsequent cycles. If entropy grows monotonically with each cycle, cycles would become less and less hospitable. Some recent cyclic proposals try to solve that by having mechanisms that dilute or reset entropy, but these are speculative and often require new physics at very high energies. Speaking of new physics, the role of yet unknown high-energy phenomena is the recurring wildcard. Many of the most dramatic endings hinge on physics we haven't tested. The detailed shape of the Higgs potential at very high energies, the behavior of gravity under quantum rules, or the existence of additional fields or dimensions. The Large Hadron Collider and its upgrades help by tightening constraints on standard model parameters and by searching for new particles. Cosmological probes help in a different way. They can indirectly rule out classes of dark energy models or pinpoint deviations from expected structure growth. The interplay of particle physics and cosmology is especially rich here. What you measure in collider experiments feeds into vacuum stability calculations. What you measure in cosmology constrains the behavior of fields at low energy and on large scales. Another thread worth unpacking is the multiverse idea. In some inflationary scenarios and in string theory's landscape, many vacuum states are possible, each with different physical constants. If the universe we observe is just one bubble in a vast multiverse, then different bubbles could have very different fates. Some might crunch, some might inflate forever, some might have vacuum instabilities. That picture reframes questions about the end. Is the end a property only of our bubble, or is it meaningful across the whole multiverse? The multiverse also raises thorny questions about testability and probability. If every possibility exists somewhere, how do you make predictions that can be falsified? Physicists address this with measures and selection effects. For instance, only bubbles that allow observers will be observed, but the technical and philosophical challenges remain active areas of research. What could tip the scales away from the current lambda-CDM expectation? Historically, there are two things: new data and new theoretical insights. Data showing a time-varying W or a value of W significantly different from -1 would require rewriting the dark energy script. Surprising signals in the CMB or the large-scale structure, inconsistent with Gaussian primordial fluctuations, or revealing anomalies from early bubble collisions, would open alternative scenarios. On the theory side, a consistent and experimentally supported quantum theory of gravity that predicts different vacuum behavior could change our expectations about the far future. Finally, a discovery of new particles that couple to the Higgs or otherwise modify high-energy behavior would change vacuum stability analyses. We should also distinguish what probable means in cosmology. When physicists say heat death is the most likely outcome under current data, it's a conditional probability. Given our best fit model and the assumption that dark energy is a cosmological constant, thermal fade-out is the prediction. It's not a definitive decree from first principles. It's the outcome of a model matched to data. That's why the quest for better measurements is so pivotal. Tightening constraints on W, measuring the sum of neutrino masses, refining the top quark mass, and probing early universe physics all chip away at uncertainty. There's an emotional texture to these scientific discussions that's worth acknowledging. Some scenarios, the Big Rip and false vacuum decay, are visceral in their imagery. Others, heat death, are hauntingly quiet. Yet the intellectual value isn't about schadenfreude at hypothetical cosmic misfortunes. Thinking through these endings forces us to test the robustness of our theories under extreme conditions, to refine how we interpret probability in cosmological contexts, and to push for experiments that reach out across scales. The fact that tiny variations in parameters could change the entire cosmic finale is a humbling reminder of both our progress and our ignorance. Practically speaking, none of these endings gives humanity a checklist of immediate action items. We can't tune the cosmological constant, stop a bubble wall, or delay proton decay. But the study of these outcomes does have tangible scientific payoffs. The same instruments and surveys that map the expansion history also map the history of galaxies, dark matter, and cosmic structure. They tell us about the earliest instance after the Big Bang. They test gravity in regimes inaccessible on Earth. The search for vacuum stability links directly to accelerator physics, motivating precision measurements that deepen our understanding of how particles get their masses. The effort to resolve these questions drives technology, data analysis techniques, and cross-disciplinary thinking that benefits many parts of physics and astronomy. Finally, there are conceptual lessons that are surprisingly practical. The end states highlight how important it is to think carefully about idealizations, like assuming an eternal de sitter future, and how sensitive conclusions can be to small theoretical assumptions. They also show why probability and measure issues matter. The way you count observers or regulate infinities changes, which predicted outcomes you consider typical. Those are not dry philosophical wrinkles. They are central to making sensible scientific statements about the universe as a whole. We've still got plenty of territory to cover: more detailed mechanisms of bubble nucleation, the nitty-gritty of observational programs, and what they're likely to achieve, the role of quantum gravity in smoothing singularities or enabling bounces, and the conceptual puzzles like Boltzmann brains and probability measures. We can also look at edge case scenarios, hybrid models that mix elements of two or more outcomes, and the latest experimental constraints that sharpen our picture. If you're curious about the math behind vacuum decay calculations, or the precise observational numbers for W and how surveys will tighten them, we can dive into those next, always keeping the picture intuitive. If you're curious about the math behind vacuum decay, don't worry. The equations themselves can be kept at arm's length, and the core idea is wonderfully simple. Picture a landscape of hills and valleys. What we call the vacuum is just one of those valleys, maybe not the deepest one available. In quantum field theory, even if you sit in a valley that seems comfortable, there's a tiny chance, thanks to quantum mechanics, that you'll tunnel through the hill and pop into the deeper valley. In the field picture, that tunneling shows up as the spontaneous creation of a bubble of the lower energy vacuum. Once formed, that bubble grows, because its interior has lower energy, and the wall separating the two vacua accelerates outward, converting what was formerly the old vacuum into the new one. Physicists boil the likelihood of such a tunneling event into a simple-looking formula. The decay rate per unit volume goes like a times exp minus b/h stroke. The a in front is a prefactor tied to many details, and the exponential term contains b, the bounce action, which encodes how hard it is to get from the false vacuum over the barrier to the true vacuum. Because the action sits in the exponent and h stroke, Planck's constant, is tiny in everyday units. Even moderately large values of b make the exponential enormously small. That's the mathematical reason why a metastable vacuum can be effectively eternal for all practical purposes. The exponent kills the probability per unit time and per unit volume. 2 points are worth emphasizing about that formula. First, the deeper and wider the barrier between the false and true vacua, the bigger b becomes, and the longer the expected lifetime. Second, gravity participates. Sidney Coleman and Frank DeLucia extended the basic picture to include gravitational effects. In some parameter ranges, gravity suppresses decay, and in others it can make decay easier. That interplay matters for cosmology because our universe isn't just a quantum field sitting in flat space. It's curved, expanding spacetime with a global geometry that affects tunneling, all of which returns us to the Higgs. The Higgs field gives particles their masses, and its potential, the landscape it lives in, could have a shape that is metastable. Measurements of the Higgs mass combined with the top quark mass tell you how that potential behaves at very high field values. The current measurements push the standard model into a curious borderland. The Higgs sits close to the line separating absolute stability from metastability. When people run the numbers inside the standard model, the lifetime for vacuum decay often comes out fantastically long, overwhelmingly longer than the current age of the universe. But the calculation is delicate. Small shifts in the measured top mass, subtle differences in how you define that mass experimentally, or the existence of new heavy particles we haven't discovered could tip the balance. That's why particle physicists and cosmologists pay attention. Better precision in the lab feeds directly into better predictions for the universe's long-term fate. You'll often see a concern phrased like this: could human experiments, say, at particle colliders, accidentally trigger vacuum decay? The short answer is no. Any process we can create on Earth is tiny compared to cosmic processes that have routinely occurred across all of space and time. High-energy cosmic rays slam into matter with energies far beyond what humans produce, and yet nothing catastrophic has been observed. If vacuum decay were easy, the universe would already have transitioned a long time ago. The likelihood is dominated by the exponential suppression in the bounce action, and everyday or laboratory energies are far too small to change that. That said, vacuum decay would be dramatic precisely because it would be instantaneous from our local perspective. The bubble wall would move at nearly the speed of light. There would be no warning. Thinking about it that way makes the idea emotionally striking, but scientifically the takeaway is practical. We should measure parameters relevant to the vacuum more precisely and continue testing for new physics that could change the potential's shape. Shifting gears to dark energy, the single number people focus on is W, the ratio of pressure to energy density for the dark energy component. If W equals -1 exactly, dark energy behaves as a cosmological constant. Its energy density is constant in time, and the expansion accelerates to a steady-state de Sitter-like future. If W differs from -1, especially if it varies in time, plenty of doors open. Quintessence models picture a field slowly rolling down its potential, like a ball in a shallow slope. Phantom models correspond to even stranger behaviors, where the effective density grows with expansion. Observational cosmology aims at pinning down whether W equals -1 exactly, or if there's a tiny tilt or time dependence. Here's how these measurements work in practice. Astronomers observe distant, standardizable candles, type Ia supernovae, standard rulers features in galaxy clustering known as baryon acoustic oscillations, and the cosmic microwave background's pattern of fluctuations. They watch how structures grow over time and how matter lenses background light. Combining these probes narrows down the possible expansion histories. Right now, the data cluster tightly around W equals -1. Deviations, if present, are within a few percent of that value. Those existing constraints already rule out many wild dark energy models, but they leave room for subtle dynamics. And when dynamics are subtle, the long-term outcome can still be qualitatively different. To get a bit more concrete about parameterizing possible evolution, cosmologists often use a simple linear model for W. A, the CPL, Chevier-Polar-Scalinder parametrization, where W, A equals W0 plus Y1 minus A, and it is the scale factor of the universe. It's 1 today and smaller in the past. Here W0 is the present value and Y governs how quickly W changes. Surveys set constraints on the pair W0, Y. The tighter those constraints become, the more we can rule out quintessence or phantom alternatives. Upcoming and ongoing projects promise substantial improvements. Wide-field imaging surveys, huge spectroscopic maps of galaxies, and more precise measurements of cosmic microwave background polarization and lensing. Which projects, several, are already changing the game. Ground-based instruments like the Dark Energy Spectroscopic Instrument, DAISY, and the Vera Rubin Observatory are mapping galaxies and supernovae over huge volumes. Space missions like Euclid have already begun their surveys, and the Nancy Grace Roman Space Telescope is expected to join in. Future CMB experiments, CMBS-4, Simons Observatory developments, will improve constraints on geometry and matter content. Together, these programs are designed to shrink uncertainties on W0 and Y to the percent level or better, which will either tighten confidence that the cosmological constant is the right description or reveal subtle departures. Because small differences in W can have enormous consequences over billions or trillions of years, constraining W tightly is a big deal. A tiny shift toward W-1 reawakens phantom energy possibilities and the Big Rip. A shift toward a time-varying W might allow dark energy to fade or reverse sign in the far future, opening up crunch or cyclic possibilities. That's why cosmologists talk about percent-level precision with a sense of urgency. It's not vanity about digits, It's about deciding which cosmic stories remain plausible. Beyond measuring W, people look for other clues that would strengthen or weaken particular futures. For example, a detected background of gravitational waves with certain spectral features could indicate that a first-order phase transition happened in the early universe. First-order transitions are the kind that produce bubbles, think of water boiling, with bubbles that nucleate and collide. If a similar bubble process occurred in the very early universe, the collisions would have generated gravitational waves that could be measured today at the right frequencies. Instruments like LISA, a planned space-based gravitational wave observatory, and pulsar timing arrays are sensitive to particular frequency bands where these early universe signatures might hide. Detecting a cosmological gravitational wave background that matches a predicted spectrum would give us a window into exotic physics and could hint at vacuum structure beyond the standard model. That connection between early universe phase transitions and potential late-time vacuum structure is subtle but important. It's a reminder that our cosmic history is a diagnostic tool. The way the universe evolved sets constraints on what was or wasn't possible in the past, and those constraints in turn restrict future behaviors. We should also return to a thornier conceptual issue: Boltzmann brains. In a universe that approaches a thermal equilibrium and persists indefinitely, rare fluctuations can randomly assemble low-entropy structures, even briefly formed brains with false memories. If such freak observers are produced more often than ordinary observers who arise through biological evolution, then our assumptions about typicality are threatened. Why should we expect to be normal observers and not random fluctuations? The resolution to this paradox is not purely empirical. It involves how you count observers and how you regulate infinite volumes and times in cosmology. Several proposed fixes exist. One is to posit that de Sitter space isn't truly eternal, maybe it decays or evolves on timescales that cut off the problem. Another is to adopt a measure, a rule for comparing infinities, that suppresses Boltzmann brain dominance. A third route is to suggest new physics at the quantum gravity level that changes the late-time thermal behavior of spacetime. None of these is universally accepted, which is why Boltzmann brains continue to be invoked as a serious conceptual constraint on cosmological models. That brings us to quantum gravity and the question of whether de Sitter space, the geometry of a universe with a positive cosmological constant, is a robust, exact solution once you include quantum gravity. String theory and related approaches have struggled to produce long-lived de Sitter vacua in a controlled way. This has led to conjectures, like the de Sitter swampland idea, which suggest that consistent theories of quantum gravity might not allow eternal de Sitter space. The swampland program is speculative and controversial, but it emphasizes a profound possibility. Maybe a pure cosmological constant is not a final answer. Instead, dark energy might be dynamic, slowly rolling toward less positive values or towards a different regime entirely. If so, the long-term fate could be different than heat death, perhaps a transition, a reversal, or some non-trivial endgame governed by quantum gravity. It's worth stressing the practical upshot. The questions that sound philosophical, is de Sitter eternal, or are we in the swampland, actually influence what experiments we build and what measurements we prioritize. If eternal de Sitter is incompatible with quantum gravity, that motivates searches for even tiny time-dependent deviations in dark energy. If the Higgs vacuum is metastable, improving top and Higgs mass measurements becomes a cosmological priority. Now consider cyclic and bounce models with a bit more detail, because they illustrate how radically different the endgame could be if new physics appears. One family of models proposes that the universe goes through infinite cycles: expansion, slow dilution, contraction, and then a bounce into a new expansion phase. The big challenge for such models is entropy. With each cycle, entropy tends to increase, and naive cycles get noisier and less hospitable. To sustain cycles, a model must either remove or dilute entropy between cycles. For example, by pushing it into degrees of freedom inaccessible to the next cycle, or by finding a mechanism that makes each new cycle begin in a low-entropy state. Various proposals attempt this. Some use extra dimensions and brain physics to shed entropy. Others invoke phases dominated by stiff forms of matter that smooth and reset conditions before each bounce. Loop quantum cosmology suggests that quantum geometric effects can prevent the singularity and produce a bounce without infinite compression. But the detailed dynamics and entropy bookkeeping are active research topics. The ekpyrotic model, inspired by string theory, imagines brain collisions that set up new expansion phases. But again, the entropy problem and matching to observations pose hurdles. All these bounce or cyclic scenarios are attractive partly because they reframe the notion of an absolute end. What looks like an end locally may be a transition that becomes a beginning under new physics. They also tend to push the hard questions into regimes where our current experiments can't yet penetrate near-singularity densities or the Planck energy scale, which is both frustrating and motivating for theorists. There are also hybrid futures to consider. The universe might follow a pattern that mixes elements of several scenarios. Dark energy could be nearly constant for many billions of years and then shift, leading to a late-time bounce or collapse. Vacuum decay could be suppressed in most of space, but become possible under high curvature, opening up localized transitions. Black hole evolution might interact with dark energy in unexpected ways if new couplings exist between fields. The point is that cosmic fates aren't binary choices written in stone. They're the outputs of models with many moving parts, and small changes in assumptions can produce qualitatively different endings. Observationally, what would scare scientists enough to change their vote away from heat death? A few dramatic possibilities come to mind. If multiple independent probes established a value of W statistically different from -1 by more than a few percent, that would force serious rethinking. If new particles were discovered at colliders that couple to the Higgs and reshape its potential, vacuum metastability calculations would change. If gravitational wave experiments detected a background consistent with bubble collisions from a first-order phase transition in the recent cosmological past, that would be a direct sign that vacuum structure is more active than we thought. Even more subtle are anomalies in the cosmic microwave background or in large-scale structure that don't fit standard inflationary predictions. Those could hint at exotic early universe physics with implications for the future. On the theoretical front, breakthroughs in quantum gravity, a consistent, testable theory that shows how de Sitter space behaves under quantum corrections, could upend current thinking. If a future theory demonstrates that eternal de Sitter is impossible, then the currently favored long-term heat death gets reinterpreted as only a transitory phase. Conversely, a robust derivation showing de Sitter is stable within quantum gravity would deepen our confidence in the quiet endgame. Meanwhile, we've got practical, concrete science to do, improving measurements of the top quark mass to better than a GeV, and understanding how to convert experimental mass definitions into the theoretical quantities used in vacuum stability calculations will reduce uncertainties in our metastability estimates. Pushing supernova surveys and galaxy redshift surveys to larger volumes and better systematics will tighten constraints on W0 and WA, enhancing our ability to detect or rule out stochastic gravitational waves over a wide frequency range, gives us a handle on early universe phase transitions. And refining CMB measurements tells us about geometry, relativistic particle content, and inflationary initial conditions, each of which feeds into the big picture story. One more strand that ties many of these threads together is entropy and information. Black holes, which carry enormous entropy proportional to their horizon area, dominate the entropy accounting of many late universe scenarios. The interplay between black hole thermodynamics, Hawking evaporation, and the cosmological horizon's entropy raises puzzles about what the most entropic state truly means for a universe with a cosmological constant. If spacetime has a maximum observable entropy, as a de Sitter horizon suggests, then questions about typicality, recurrence, and fluctuation become technical constraints on cosmological models. Resolving these requires us to blend quantum field theory, general relativity, and statistical mechanics in ways that are still being worked out. Another area where progress could dramatically change our expectations for the cosmic end. None of this is merely mental exercise. The same tools, particle accelerators, precise astrophysical surveys, gravitational wave detectors, that let us test these ideas are being built and upgraded now. Improving data helps rule out whole classes of doom scenarios or raises interesting tensions that drive new theories. The science advances because we keep asking which measurements matter for which outcomes, and then build instruments designed to answer those exact questions. There's also a crucial methodological lesson here. Predicting the far future of the universe is not a matter of guessing which scary ending you like best. It's a disciplined activity of mapping models to measurable quantities, pushing uncertainties down, and letting the data tip the scales. Some endings are intrinsically unobservable from inside our bubble. If a bubble nucleates beyond our horizon, we'll never see it until it's at our doorstep. But the parameters that control those possibilities often leave fingerprints we can measure today. We'll keep exploring those fingerprints. Next, we can dig into more specifics about how surveys quantify dark energy, the statistical tools used, how systematics are controlled, and what a hypothetical detection of W not equal to -1 would practically mean for the timeline of the universe. We can also unpack the finer points of vacuum decay calculations, why the top quark mass precision matters, what theoretical uncertainties are hardest to reduce, and how future colliders could change the story. Alongside that, it's worth tracing what each scenario would look like observationally in human-accessible timescales, and which speculative escape routes advanced civilizations might plausibly attempt if they ever faced resource constraints stretched over eons. We left off at the point where the big future questions narrow down to two kinds of action: better measurements and better theory. Let's start with the measurements, because that's where the rubber meets the road. Cosmologists don't just eyeball the sky and guess. They design experiments to tease apart tiny differences in how the universe expands and how structure grows. Those tiny differences are the fingerprints that tell us whether dark energy is a cosmological constant, a slowly changing field, phantom energy, or something else entirely. But getting those fingerprints requires careful statistical work, attention to messy systematics, and multiple complementary probes, so that independent weaknesses don't line up and fool us. At the most practical level, surveys collect three broad kinds of information: distances, clocks, and maps. Distances come from standard candles like Type Ia supernovae and standard rulers like the baryon acoustic oscillation feature, basically cosmic yardsticks imprinted when the universe was young. Clocks come from how fast structures form and how gravitational potentials change over time, which you can measure via galaxy clustering and gravitational lensing. Maps are simply large volume surveys that tell you where matter is and how it clumps across cosmic time. When you stitch all three together, you get a detailed picture of the expansion history and the growth history, and that's what pins down parameters like W. But each probe has its own nuisances. Type Ia supernovae are not perfect candles. Their observed brightness depends on host galaxy properties, intervening dust, calibration of instruments, and sample selection effects. Careful teams spend years improving calibration, understanding how host metallicity and age affect brightness, and correcting for biases. Baryon acoustic oscillation measurements are robust geometrical tools, but they require big samples and precise redshifts. They're affected by galaxy bias, the fact that galaxies are messy tracers of underlying matter, and by nonlinear physics on small scales. Weak gravitational lensing, mapping how large-scale structure bends light, is incredibly powerful because it directly probes the mass distribution, but it's sensitive to point spread functions in images, shape measurement biases, and photometric redshift uncertainties. All of these systematics are understood to varying degrees, and survey designers work to both reduce and quantify them, because an unmodeled systematic can masquerade as a subtle departure from W equals -1. The statistical toolkit cosmologists use is well honed. They build likelihood functions that connect model predictions to data, include nuisance parameters for systematics, and explore parameter space with Monte Carlo methods to produce credible intervals. They also use Fisher matrix forecasts to estimate how well a planned experiment could constrain parameters, and blind analyses that prevent experimenters from biasing results toward trendy outcomes. That combination of rigor and redundancy is why the community trusts the current result, that W is very close to -1, while still seeking improved precision. So what would it look like, practically, if future surveys convincingly detected W not equal to -1? Tiny deviations would change more than the number in a text box. They'd rewrite our long-term story. If W were measured to be, say, -0.95 or -1.05, and that result held up with multiple probes, theorists would be forced to accept that dark energy is not simply a cosmological constant. A detection with W-1, say -0.95, would point toward quintessence-like models, a field slowly rolling down its potential. That typically means dark energy's influence could change with time. It might fade or grow less dominant, opening possibilities where expansion slows or reverses in the far future. That would resurrect crunch or cyclic possibilities in principle, though not necessarily predict them concretely without additional modeling. A measurement of W-1, say -1.05, would be more alarming because it nudges us toward phantom energy and the Big Rip family of ends. The severity depends on how far below -1 and whether W evolves. If W is just a hair below -1 and doesn't change, the timescale for a rip is typically so long that it's not an immediate existential issue. If it's substantially below -1 and continues to remain phantom-like, the rip could be sooner, tens of billions rather than trillions of years, and that would make the Big Rip a viable long-term fate. Importantly, the current errors are small, but not small enough to rule out small departures, which is why upcoming projects aim for percent-level constraints or better. Improving those constraints is the job of a generation of instruments. The Vera Rubin Observatory will deliver vast imaging data ideal for weak lensing and transient discovery. DAISY maps millions of galaxy redshifts to trace large-scale structure. Euclid and the Nancy Grace Roman Space Telescope bring space-based stability for precision photometry and infrared observations. Future CMB experiments like CMBS-4 will refine cosmological parameters and neutrino mass constraints that couple into dark energy inference. Combining these datasets is crucial because each one's systematics are different. If several independent, differently biased datasets point to the same small departure from W equals -1, confidence grows. Now let's pivot to the quantum side. Vacuum decay. We described tunneling in qualitative terms, and now the practical question is how to make that abstraction concrete. The bottom line is that the lifetime of a metastable vacuum is extremely sensitive to parameters, so improving laboratory measurements can directly inform cosmology. The Higgs boson mass and the top quark mass are the key players here because they set the renormalized shape of the Higgs potential at high energies. The current central values put the standard model in a metastable region, but the answer hinges on uncertainties in the top mass and on unknown higher energy physics. This is where particle colliders matter. The Large Hadron Collider's measurements of the Higgs were revolutionary, but to shrink the shadow of uncertainty further you need either a high-luminosity upgrade HLLHC, which will collect far more data, or a next-generation collider like the proposed Future Circular Collider, FCC, or an electron-positron Higgs factory, the ILC or CLIC concepts. These machines would measure the Higgs couplings with great precision and clarify the top quark mass to the degree needed for sharper vacuum stability calculations. There are technical subtleties. Different definitions of top mass used in experiments must be connected to theoretically clean masses, but progress is being made. The clearer the lab picture, the better we can say whether the Higgs potential has a deep basin we might tunnel into. A related practical reassurance is that we don't need to be scared that human-made experiments could trigger vacuum decay. Cosmic rays routinely collide at energies higher than any collider, and in the history of the universe, lots of such events have occurred without catastrophe. If decay were easy to trigger, it would already have happened somewhere in our past light cone. So while metastability is a live theoretical possibility, earthly experiments are not the danger. Could we get any astrophysical warning of vacuum decay? Unfortunately, no reliable early warning signs exist. If a bubble nucleates beyond our horizon, it can expand for eons before reaching our patch, and the wall moves at nearly light speed. Once it crosses into our future light cone, we'd have no advance notice. That put a premium on improving the precision with which we map the Higgs potential on paper, because that's the only practical way to say anything definitive. There's another observational window worth highlighting: gravitational waves. First-order phase transitions, the kind that proceed by bubble nucleation, can generate stochastic gravitational wave backgrounds when bubbles collide and their walls and the ambient plasma stir up bulk motion. Upcoming gravitational wave observatories will be sensitive to different frequency bands. LISA, a space-based interferometer planned for the mid-2030s, targets millihertz frequencies well-suited to transitions at energy scales below about 100 TeV. Pulsar timing arrays, PTAs, like nanograv, EPTA, and the International Pulsar Timing Array probe nanohertz frequencies, and have recently reported signals that some interpret as a stochastic background consistent with supermassive black hole binaries. But others have pointed out that certain early universe phase transitions or cosmic string networks could also produce backgrounds in that band. While no firm cosmological detection has been confirmed yet, the growing gravitational wave dataset could eventually reveal a background consistent with past bubble collisions. Finding such a signal would tell us that the vacuum landscape is active and that similar physics might be relevant to late-time vacuum structure. Another subtle but important observational lever is neutrino mass. The sum of neutrino masses affects structure formation on small scales and is partially degenerate with parameters that also influence dark energy constraints. Improved CMB measurements and large-scale structure surveys aim to pin down neutrino mass to a degree that removes this degeneracy. That in turn tightens dark energy constraints and indirectly helps settle long-term fate issues. While experiments chip away at uncertainties, theorists wrestle with conceptual problems that shape how we interpret results. One such difficulty is the measure problem in cosmology. When you have potentially infinite space and possibly infinite time, how do you meaningfully assign probabilities? Different prescriptions yield different assessments of which events are typical. This is not trivial math technicality. It changes how we think about things like Boltzmann brains or the distribution of vacuum energies across a putative multiverse. Boltzmann brains deserve a bit more unpacking because they're where physics and philosophy collide. Imagine a very long-lived universe in which everything settles into thermal equilibrium. Random fluctuations in that equilibrium will occasionally produce complex, low-entropy structures, even a brain with transient consciousness and a semblance of memories. If your cosmological model predicts that these random brains outnumber normally evolved observers by enormous factors, then you face a weird paradox. Why aren't you such a fluctuation? The most straightforward way out is to adopt a theory that prevents the dominance of Boltzmann brains. For example, by having de Sitter space be unstable and decay on timescales short enough to avoid the problem, or by choosing a probability measure that de-emphasizes such rare fluctuations. None of the solutions is universally accepted, which is why Boltzmann brains continue to be a hot topic. They're not an immediate physical threat. They're an argument that some cosmologies are conceptually problematic and thus less attractive. Another theoretical arena under active debate is whether true, eternal de Sitter space is compatible with a consistent theory of quantum gravity. Some lines of thought, including parts of the string theory, swampland, program, argue that long-lived de Sitter vacua are hard to construct in a way that's consistent with quantum gravity. If that's right, it points to the idea that the cosmological constant we infer might not be a forever constant, but the temporary value of a field slowly evolving or destined to decay. This would tilt the long-term balance away from a boring heat death and towards some future transition. The swampland ideas are speculative and contested, but they have the useful effect of motivating precise measurements of anytime dependence in dark energy. An observed drift would lend credence to dynamical dark energy models and to the notion that de Sitter is transient. Let's step back and consider the kinds of far future signatures different endings would leave in humanly accessible times. If the universe were heading for a big rip and the timescale were cosmologically near, we'd be able to detect an accelerating expansion rate that departs from a cosmological constant in a very specific way. Not just a different W0, but a rapidly changing W. Ace. Observationally, this would show up as supernovae at different redshifts, deviating from the lambda CDM distance redshift relation, as large-scale flows changing in character, and as structure growth being suppressed in a way inconsistent with other measurements. If such deviations were robust and increasingly confirmed, the Big Rip would move from science fiction scare story to a live model we'd have to take seriously. If the universe were to head for a big crunch, we'd observe deceleration. The expansion would slow, possibly stop, and reverse. Galaxies would eventually shift from redshifted to blueshifted in a statistical sense, and the cosmic microwave background's temperature would increase over long time. Again, this would be a long process, not sudden, but the observational signature is clear in principle. Vacuum decay, as we said, is fundamentally different. It leaves essentially no observational warning. For that reason, lab measurements of high-energy parameters are the most realistic path to improved understanding. Gravitational wave hints of early phase transitions would be suggestive that bubble physics occurs in nature, making vacuum decay scenarios more plausible in principle, but they'd still not tell us whether our vacuum is on the brink. Let's entertain, briefly, what a technologically advanced civilization might try to do if it faced resource starvation in the face of heat death or slow fading. This is speculative and mixes physics with engineering imagination, but it's useful for clarifying limits. One idea, proposed in a conceptual form by Freeman Dyson, is to have civilizations go into an extreme hibernation mode, doing computations and activities ever more sparsely, so that subjective experience stretches arbitrarily long even as thermodynamic resources dwindle. The catch is that in a universe with a strict de Sitter horizon, there's a finite informational and energetic budget accessible to any observer. Cross and Starkman later argued that in a true de Sitter universe, no strategy can yield infinite subjective time because heat death fixes a finite, limiting amount of free energy. Reversible computing and adiabatic strategies can defer dissipation, but Landor's principle, the idea that erasing information requires a minimum amount of heat dissipation, still enforces limits if irreversible operations are required. In short, cleverness can extend lifetimes and preserve complexity longer than naive estimates, but many models suggest that infinity is out of reach under a strict cosmological constant. Civilizations might also attempt to relocate to the last gravitationally bound systems. For instance, to migrate toward the most massive bound cluster or to harvest energy from black holes. Black holes are intriguing resource candidates because they store enormous amounts of mass energy and, in principle, could be used as engines for extracting energy via accretion or Penrose-like processes. One speculative proposal is to construct Dyson swarms to capture available starlight for as long as stars shine. But again, these are adaptations to local conditions and don't change the ultimate fate dictated by cosmology. They illustrate, however, that hypothetical intelligent actors would be constrained by the same physical laws we study, and that any concrete survival strategies depend critically on what the cosmological parameters actually are. Another fascinating class of proposals revolves around making structures or computations inside black holes or near them. Because black holes have different causal structures, some have speculated about the feasibility of storing information or conducting computations in exotic near-horizon environments. Most of these ideas bump against practical engineering impossibilities and unresolved theoretical issues. What happens at singularities, the information paradox, whether advanced civilizations could access the necessary conditions. But they're worth thinking about because they force us to combine thermodynamics, information theory, and general relativity, the same blend that determines cosmic fate. We should also mention that new theories of gravity or new particles could change the calculus dramatically. Imagine a new long-range force that couples to dark matter in an unexpected way, or a light scalar field that modifies gravity on large scales. Those possibilities would alter structure growth and the expansion history in measurable ways. Equally, if a new particle couples to the Higgs and stabilizes its potential at high energies, the metastability story could evaporate. That's why experiments across the energy scale, from colliders to dedicated dark matter searches to precision cosmology, are complementary. Dark energy surveys constrain cosmological scale behavior. Particle experiments test microscopic interactions. Jointly, they narrow the landscape of plausible fates. There's also intellectual value in mapping not only the likely ends, but the robust features that survive across many models. For example, almost every plausible long-term scenario predicts that stars will exhaust their nuclear fuel and that life, as we understand it, depends on gradients and will be affected by their decline. That commonality reframes cosmic futures in ways that are relevant to questions about the rarity of life and the timing of intelligence. Even if the detailed cosmic end differs rip, freeze, or crunch, the near term, by cosmic standards, window for life and observation exists and is precious. That's part of the reason why cosmology, while mapping far futures, also underlines the contingency and finiteness of our observational possibilities, bringing the discussion back to observation and theory coordination. The most informative near-future outcomes will come from narrowing down W and pinning down vacuum stability. Achieving a percent-level measurement of W0 and Wa would either reinforce the cosmological constant picture or definitively push us toward dynamical dark energy. Reducing the top quark mass uncertainty to better than a GV and understanding theoretical mass definitions would strike a big blow for or against Higgs-mediated vacuum metastability. Detecting a stochastic gravitational wave background consistent with early universe phase transitions would tell us that structural phase changes happen in nature, prompting a reevaluation of vacuum dynamics. Each of these observational wins would likely spawn waves of theoretical follow-up, producing clearer stories about the long-term fate. One technical caution is worth repeating: all these inferences are conditional. Saying heat death is the most likely future means heat death is the most likely given our current best model and the current observational constraints. Discoveries and theoretical advances can change that assessment. The progress of science is exactly the process by which such conditional predictions get refined. That's why the community aims for redundancy, multiple instruments, multiple lines of evidence, and multiple theoretical techniques. When independent chains converge, confidence grows. Before we move on, it's interesting to consider edge case scenarios that often captivate imagination, though they're less mainstream in technical literature. Could the universe undergo a phase transition that doesn't fully destroy structure, but instead alters constants slightly, leaving chemistry intact but changing the rules of computation? Could quantum gravity prevent singularities and replace them with complex, information-rich transitions that preserve some memory of the prior universe? Could there be rare regions that avoid the general trend and maintain low entropy pockets for extremely long times? These questions are speculative but not nonsense. They're invitations for theorists to create self-consistent models and for observers to think creatively about signatures. For example, if a small change in particle masses occurred, biology and chemistry would be sensitive in different ways. Some molecules might no longer be stable, some reaction rates would change. That creates a spectrum of possible survivability, outcomes ranging from total annihilation of complexity to a reshaping of the chemical landscape in which life might adapt. Thinking this way underscores the degrees of freedom involved. Cosmic ends aren't just about geometry and temperature. They're about the detailed microphysics that underwrites chemistry and life. Another speculative angle is cosmological speculation about information and whether the far future could be dominated by weird information theory phenomena. If black holes dominate late-time energy budgets, and if black hole evaporation is the last major thermodynamic process, the question of how information is conserved and processed at that stage becomes pressing. Debates about black hole information paradox, firewall proposals, and holographic principles aren't just abstract. They shape plausible narratives for the very late universe and whether memory of earlier epochs can persist in subtle correlations. All of this returns us to one practical point. The science of the cosmic end is not merely a catalog of horrors. It's a live research program that connects particle physics, astronomy, gravitational wave science, thermodynamics, quantum information, and philosophy. Whether the final chapter is an abrupt vacuum flip, a slow fade to cold, or a collapse followed by a bounce depends on precise measurements and ambitious theory. The next decades of telescopes, gravitational wave detectors, and colliders are therefore not just about discovery for its own sake. They're the instruments by which we learn which cosmic endings remain plausible. Let's close this segment without closing the story. We've walked through how surveys and experiments pin down the parameters that decide fates, why tiny deviations matter, how vacuum decay calculations depend on lab-measured particle properties, and how gravitational waves can reveal the presence of bubble-like physics. We've touched on Boltzmann brains and measure problems, on how advanced civilizations might attempt to adapt, and on speculative ways new physics could change the endgame. Up next, we can dig deeper into any of these threads. The specific ways future surveys will tighten constraints on W, the computational formalisms used in vacuum, decay rate estimates, and their sensitivity to experimental inputs, or the most promising signatures that would force a major rewrite of the cosmic narrative. Which direction would you like to explore further? Okay, let's pick up that thread and get concrete. If you want to move from what might happen to how we'll know, the immediate next step is to look at the experiments and calculations that can actually shift the odds. There are two broad pathways to changing our picture of the cosmic end. Better measurements of the universe's large-scale behavior, which tell us about dark energy and the expansion history, and better measurements of microscopic physics, which tell us about vacuum stability and whether sudden quantum changes are possible. Those two directions are complementary. One looks outward across the sky, the other looks inward at the particles that make up everything we see. I'll walk through both in plain terms, explain why tiny improvements matter so much, and then show how theory ties everything together, including the conceptual wrinkles that make cosmology oddly philosophical. First, the observational side. Imagine the cosmos as a detective scene. The evidence we collect about how the universe expands and how structure grows is the set of fingerprints that point to one ending rather than another. The three most powerful kinds of evidence are distances, clocks, and maps. Distances, Type Ia supernovae, are our best standard candles. They're bright stellar explosions that, once properly calibrated, give you a pretty reliable measure of how far away something is. Pair that with standard rulers, the imprint of sound waves in the early universe, baryon acoustic oscillations, and you get a geometric picture of how far apart things are at different times. Small deviations in those distance measures reveal whether expansion is changing in the way a cosmological constant predicts or in some other way. Clocks. The universe itself provides clocks through the growth of structure. Gravity makes matter clump into galaxies and clusters at a rate that depends on how fast the universe is expanding and on what forces are in play. If dark energy were changing over time, it would leave a fingerprint in the rate at which structures grow. Measurements of galaxy clustering and gravitational lensing, how foreground mass distorts the shapes of background galaxies, act as cosmic stopwatches. Maps, wide, deep maps of the sky, millions of galaxies with their distances, let us compare shapes and patterns across time. That helps disentangle degeneracies, those frustrating cases where two different physics explanations produce very similar observations. Big maps give variety and statistical power. Why do tiny changes matter? Because cosmological effects integrate over enormous time and volume. A small percent-level difference in the dark energy parameter W can change the fate of the universe in the very long run. Whether dark energy stays constant, slowly fades away, or grows stronger. That's why the community spends a lot of energy trying to squeeze down uncertainties on W and on any time dependence in it. Several major projects are designed for exactly that purpose. The Vera C. Rubin Observatory will scan the sky in unprecedented detail, discovering supernovae and measuring the shapes of billions of galaxies for weak lensing. The Dark Energy Spectroscopic Instrument, DAISY, and similar spectroscopic surveys map the three-dimensional positions of millions of galaxies, which sharpens baryon acoustic oscillation measurements and the growth of structure information. Space missions like Euclid and the Nancy Grace Roman Space Telescope bring space-based stability and infrared sensitivity, which are especially valuable for seeing faint, distant galaxies and for controlling certain systematics that ground-based telescopes struggle with. Future CMB experiments, sometimes grouped under names like CMBS-4, aim to improve knowledge of the early universe and neutrino properties, which in turn reduces errors on key cosmological parameters. Those experiments aren't just flashy names. They are designed specifically to reduce the uncertainties that make the difference between heat death and some more exotic ending. If multiple independent probes converge on W equals -1 to very high precision, the simplest, quiet long-term picture becomes much more secure. If instead they consistently find W differs from -1, even by a percent or two, the implication is enormous. Dark energy would probably be dynamic, and that opens doors to quintessence-like scenarios or even phantom energy if W is measurably less than -1. So how tight do we need to make these measurements? There's not a single sharp threshold because what matters is the model you compare to. But roughly, percent-level precision on W0, the present value of W, and good constraints on WA, a simple way to capture how W might change over time, would either cement the cosmological constant picture or force us into new physics. Getting to those levels means huge datasets and scrupulous attention to systematics, the little measurement errors and biases that can masquerade as a physical signal. That's why projects combine different techniques. Supernovae, baryon acoustic oscillations, weak lensing, and CMB all have different systematic weaknesses. If all of them point the same way, the result is robust. That covers the cosmic scale observations. Now let's switch to the particle scale measurements that affect vacuum stability. This is where collider physics meets cosmology. The central actor here is the Higgs field, the field responsible for giving elementary particles their mass. The shape of the Higgs potential at very large field values determines whether our vacuum is the deepest valley in the landscape, stable, or a local valley that could eventually tunnel to a deeper one, metastable. Two laboratory-measured quantities matter most: the Higgs boson mass, which we have measured with good accuracy at the LHC, and the top quark mass, which we also measure but with tricky nuances that I'll unpack. Small shifts in the top mass, at the level of a fraction of a percent, can change the theoretical inference about whether our vacuum is stable, metastable, or on the knife's edge in between. Why so sensitive? Because the calculation involves extrapolating the behavior of quantum fields to energies vastly higher than what we directly probe. The way the Higgs self interacts, and how it feels the top quark's presence affect the shape of its potential at those high values. The math is precise, but the inputs must be nailed down. That's why future colliders are more than just particle-hunting toys. A high-luminosity upgrade to the LHC, HLLHC, will collect far more Higgs events, reducing uncertainties in its mass and couplings. Proposed machines like an electron-positron, Higgs factory, would provide cleaner conditions for very precise measurements. Larger machines, such as a future circular collider, could push the energy frontier and reveal heavy particles that we haven't yet seen, and those could change the high-energy behavior of the Higgs potential altogether, achieving an experimental uncertainty on the top mass well below a GeV, and understanding how that experimental number maps to the theoretical mass parameters used in stability calculations is a central technical challenge. It's important to underline a reassuring practical detail. We don't need to worry that our accelerators could trigger vacuum decay. The energies created here on Earth are tiny relative to the total spacetime volume of the universe that has been sampled by natural, high-energy processes, cosmic rays, and collisions in stars. If vacuum decay were easy to trigger, it would already probably have happened somewhere in our past light cone. The issue is not that human experiments introduce new risks, but that they help us measure the parameters that tell whether the risk is theoretically present at all. That brings up the core mathematical reason metastability is often safe in practice. The decay rate for tunneling is exponentially suppressed. In plain terms, the chance per unit time and per unit volume that a bubble of the true vacuum forms is something like a profactor times exp minus b/h stroke, where b is a number called the action for the tunneling solution and h stroke is a tiny constant. If b is large, that exponential kills the probability so thoroughly that the vacuum is effectively eternal on timescales far longer than the age of the universe. Small shifts in parameters change b and therefore the lifetime by absurd factors, which is both why precise measurements matter and why metastable can be practically the same as stable for all intents and purposes. A different observational tracer to watch is gravitational waves. When phase transitions happen in the early universe via bubble nucleation, the cosmological cousin of boiling water where bubbles form and collide, the collisions and the stirred-up plasma can produce a background of gravitational waves. Space-based detectors like LISA will be sensitive to some of these possible frequencies. Pulsar timing arrays, the networks of millisecond pulsars monitored for tiny timing shifts, probe much lower frequencies, and have recently reported hints of a stochastic background, although the leading interpretation right now is that the loud signal is from many supermassive black hole binaries merging across the universe. Still, the broad point stands. A detection of a gravitational wave background consistent with an early universe first-order phase transition would be a smoking gun that bubble physics actually occurs in nature. That would make vacuum structure questions more than purely academic. It wouldn't necessarily mean our vacuum will decay tomorrow, but it would show that cosmological transitions are real processes and not merely fanciful mathematical possibilities. Now, beyond the nuts and bolts of measurement, there are deep conceptual issues that shape how we think about probabilities in cosmology. One of the most discussed is the measure problem. When you have potentially infinite space and possibly infinite time, how do you meaningfully say, this outcome is more likely than that one? Different ways of regularizing the infinities give different answers. That might sound like hair-splitting, but it becomes vital when you ask questions like, are we typical observers? Or do Boltzmann brains outnumber ordinary brains in the far future? Boltzmann brains deserve a clear and gentle explanation because they're where physics begins to bump hard against how we reason about observation. Imagine a universe that settles into a steady, high-entropy state and then persists for an arbitrarily long time. Random quantum fluctuations will occasionally produce unlikely, low-entropy lumps sometimes even something as complex as a brain with fleeting memories. Given infinite time, the number of these freak observers could be huge, potentially vastly exceeding the number of observers who evolved through ordinary cosmological and biological history. If that theoretical counting were faithful to the physics we inhabit, it would mean that it's overwhelmingly likely you are one of those random fluctuations, which seems absurd. The most common way out is to adopt cosmological models or probability measures that avoid Boltzmann brain dominance. That could mean the de Sitter state isn't truly eternal. Perhaps it decays on timescales that make such fluctuations negligible. Or it could mean we choose a measure that discounts late-time fluctuations. Or it could indicate that our theoretical framework for probability in cosmology needs further refinement. The point is not that Boltzmann brains are a physical threat. They are a litmus test for whether a cosmology makes sense in a probabilistic way. A related theoretical current is the swampland program in string theory. It's a technical-sounding phrase, but the basic idea is straightforward. Not every mathematical proposal that looks okay at low energies can be embedded consistently into a theory of quantum gravity. Folks studying string theory have cataloged criteria that separate the landscape of low-energy effective theories that could come from quantum gravity from the swampland of those that cannot. One of the conjectures arising from that program suggests that truly eternal de Sitter space might be hard to realize in a consistent quantum gravity theory. If that conjecture were correct, it would encourage the view that the cosmological constant is not truly constant, but instead is the temporary behavior of a field that will evolve, possibly changing the long-term fate. The swampland idea is still speculative and debated, but it underscores that the ultimate fate may hinge on quantum gravity considerations we don't yet fully understand. Let's take a moment to consider how different futures would actually look from the perspective of observers like us, months to billions of years before the end. That's useful because it separates the emotionally dramatic from the physically detectable. If a big rip were on the menu, and the rip were imminent on cosmic timescales, meaning within tens of billions of years rather than trillions, we would see a pattern of observable signatures build up. Galaxy clusters would start to lose coherence, internal galactic motions would become weird, and stellar systems would eventually fail to hold together. In practice, we could detect the accelerating expansion deviating from the cosmological constant expectation well before the ripping of atoms occurred, because those deviations have to exist to cause the rip. A big crunch would be preceded by a slowdown and then reversal of expansion. The redshift distance relation for distant objects would change sign in principle, and the cosmic microwave background temperature would begin to increase over cosmological times. These are gradual signals that could be tracked. Vacuum decay gives you, by contrast, no advance warning. A nucleated bubble wall expands at nearly the speed of light, so when it reaches a region, the change is effectively instantaneous in local time. The only way to learn about your vacuum's risk is by measuring the high-energy inputs that determine its stability. If you like imaginative, speculative problem-solving, there is a literature about what advanced civilizations might do if cosmic conditions become extremely scarce. These proposals are not blueprints. They're more like thought experiments that illuminate physical limits. Freeman Dyson once argued that civilizations could slow down their subjective time by performing fewer operations, and so possibly achieve arbitrarily long subjective lifetimes even as energy supplies dwindle. Later analyses pointed out that with a true cosmological horizon and a finite available energy, those tricks have finite payoffs. Another class of ideas involves migrating toward the last gravitationally bound systems, gathering into galaxy clusters or around massive black holes, to maximize accessible resources for as long as possible. Some think about extracting energy from black holes via the Penrose process or by feeding matter into them and capturing energy from the outgoing radiation. In all these schemes, Landauer's principle still bites. Erasing information consumes energy, so irreversible computation has a thermodynamic cost that sets limits. Reversible computing can reduce dissipation, but it doesn't magically produce free energy. These ideas are interesting because they force us to reckon with physical constraints on survival and information processing in extreme conditions. They show what can be stretched and what cannot. There are also fascinating edge case physics ideas worth a word. Could new particles or forces change the story? Certainly. A new light scalar field that couples to the Higgs could stabilize its potential and remove the metastability worry. A previously unknown long-range force could modify how structure forms and alter the inferred dark energy properties. A phase transition in some hidden sector could dump energy into radiation at late times and thereby change expansion history. Those are not wild fantasy. They're concrete possibilities that experimentalists try to test via colliders, dark matter detectors, and cosmological probes. The fact that discoveries at the smallest scales can change cosmological predictions is one of the striking features of modern physics. The very large and the very small are connected. Let's return to gravitational waves briefly, because they're an exciting frontier for signatures of cosmic phase transitions. When bubbles form and collide, they create moving stress energy that shakes the spacetime fabric. The resulting gravitational wave background has a characteristic frequency and amplitude that depends on the energy scale of the transition and the dynamics of the bubble walls and surrounding plasma. LISA will be sensitive to millihertz frequencies, which correspond to transitions at energy scales accessible to some beyond standard model theories. Pulsar timing arrays work at nanohertz frequencies and are sensitive to supermassive black hole binaries and to some cosmic string networks and very low-frequency phase transitions. If future gravitational wave data were to show a spectrum inconsistent with astrophysical sources and matching the predictions for a cosmological phase transition, that would be a huge discovery, and it would feed back into how we think about vacuum structure and late-time risks. There's one more conceptual topic that ties together many of these threads: the anthropic principle and multiverse thinking. If inflation or string theory allows many vacuum states, each with different low-energy constants, then our observed constants might be selected by the requirement that complex structures and observers can exist. That perspective reorients some questions from "why does the cosmological constant have this value?" to "among the set of possible values, in which ones does life arise?" Anthropic reasoning can be controversial because it seems less predictive. It can explain why we see certain things but doesn't always make sharp, testable predictions. Nevertheless, when combined with probabilistic measures over the multiverse, it can provide a statistical framework for why certain cosmic parameters are in the narrow ranges that allow galaxies, chemistry, and observers. If correct, anthropic reasoning would change how we discuss the cosmic end. Some vacuum states might be far more common than others. Some might be more likely to produce long-lived observers, and that would affect how we assign typicality. That in turn loops back to the measure problem. If you have an infinity of regions, how do you compare how many observers of one type exist to how many of another? The answer matters for whether Boltzmann brains swamp ordinary observers or not. It's a technical and philosophical knot. People tackle it with cutoffs, with different regularizations of eternal inflation, and with thought experiments that test whether a proposed measure produces sensible predictions. It's one of those areas where cosmology acts like philosophy with the math turned on. We should also acknowledge what's impossible. We can't influence the cosmological constant, or trigger a bubble of true vacuum, or halt the evaporation of a black hole with any technology we can imagine without rewriting the known laws of physics. That means these cosmic fates are not things to plan for in the same way you might plan for a natural disaster on Earth. They are, however, motivations for scientific inquiry. Each scenario is a pointer to physics we don't fully understand. Studying them improves our understanding of quantum fields, gravity, thermodynamics, and the early universe. The scientific effort to pin down the future of the cosmos has practical side benefits. It pushes instrumentation, data analysis, and theory in directions that produce more generally useful knowledge. So where does this leave us in practical terms? We can list concrete targets for the next decades that will materially narrow the range of plausible cosmic endings. Push measurements of W and its time dependence toward percent-level precision or better by combining supernova surveys, galaxy redshift surveys, weak lensing maps, and improved CMB observations. If W is exactly -1 within tight errors, that strongly favors the heat death story under current assumptions. Improve the precision and theoretical clarity of the top quark mass and Higgs coupling measurements. That requires both new data from colliders and careful theoretical work on how to interpret experimental mass measurements in the framework used for stability calculations. Search for and characterize stochastic gravitational wave backgrounds across a range of frequencies. A cosmological detection consistent with a first-order phase transition would reshape thinking about vacuum structure. Continue sensitive searches for proton decay and rare processes that influence the late-time inventory of baryonic matter. Results affect the chemical future of the universe. Improve neutrino mass constraints via cosmology and lab experiments, because neutrinos influence structure formation and thus play a role in disentangling dark energy effects. Pursue theoretical progress in quantum gravity and in understanding de Sitter space. Whether truly eternal de Sitter vacua are consistent with quantum gravity could change our qualitative expectations. Each of these items is actionable, testable, and tied to existing or planned experiments. That's the right way to think about cosmic endings, not as unverifiable doomsaying, but as hypotheses that can be sharpened, tested, and in many cases ruled out. Let's finish with the human side of the picture, because these cosmic endings also pose philosophical and cultural questions. Knowing about possible ends, violent tears, slow fades, sudden quantum flips, alters how we think about time, contingency, and the place of intelligence in the cosmos. It can make the present moment feel uniquely valuable in a new way. The conditions that allow complex life, chemistry, and precise cosmological observation might be transient on the largest timescales. That's not a cause for despair. It's a motivation for curiosity. The very fact that we can ask these questions and design experiments to address them is a testament to what science can do. Turn seemingly metaphysical questions into precise investigations. In the end, many of the most chilling cosmic scenarios are not imminent dangers, but rather puzzles that compel us to learn more about the universe's deepest laws. Whether the final chapter is a quiet fade into cold darkness, a sudden rewiring of physics, a collapse and rebirth, or something else entirely, the path to knowing runs through careful observation, precise measurement, and disciplined theory. That's the reassuring part. Wherever the universe is heading, the same curiosity that let us discover its expansion and its accelerating behavior puts us in a position to understand, and perhaps, in small ways, to prepare our minds for the answers we'll eventually find.